Well, good afternoon, everybody. It's a great pleasure to welcome a former colleague, Catherine Heymans, back, who's done us proud by doing fabulous work subsequently. Catherine had got a degree in Oxford, then for her first postdoc came here to Heidelberg. Years work on things like gems and composite 17 related issues. She then went for a couple of years to British Columbia before going to Edinburgh, where she's still now, doing gravitational lensing in dark things by any means necessary, and where she runs an army with her starting grant here. So welcome.
Thank you. Thank you very much. It is an absolute delight to be back in Heidelberg. I left in, I think, 2005, and I haven't been back since. So it was very exciting last night to come along and see my old house and all those exciting things. As Hans said, I've been doing lots of things scientifically since I left. But I've also been quite busy on the personal side of things. I've had 3 kids since I was last here, and they keep me very busy. And I've decided that kids are actually quite useful in science because they give you a very interesting insight, a different insight into science than you would expect. There was a big conference in Edinburgh. And unfortunately, there was a bit of a childcare crisis, so it meant that child number 2 had to come with me to give my talk, and he was sat really grumpily in the front row. So I was in full flow, and I was about to present the dark matter map that you can see behind me. This is the largest map of dark matter that we've ever made. And I was just about to get to this point, full flow, when a really familiar voice came out of the audience, and I looked around, and he jumped up and he shouted out really loudly, "My mummy doesn't know what she's talking about." It was absolutely mortifying, and I'm hoping that none of you are going to heckle me like that this evening.
We'll take it a notch down.
But actually, sort of reflecting on this moment in my career, I've realised that actually he was being quite astute. For a 4-year-old boy, he's really being quite astute. In the last few decades, cosmology has come on in leaps and bounds, thanks to the Planck satellite observations of the cosmic microwave background. We know to exquisite precision the components of our universe. We know how much dark matter there is, how much dark energy there is, how many baryons there are. We know this to exquisite precision. But we really don't understand the nature of this dark universe. We have our models for our dark matter particles. We know that our best model is a weakly interacting matter particle, but we haven't found one of these particles. And indeed, sort of the best, most compelling theory that people have been backing so far, that it's a supersymmetric particle, is starting to look weaker and weaker, because it's expected that the Large Hadron Collider would have found that particle by now, if that was the case. And then we've got this mysterious dark energy, some mysterious source of energy in the universe that's fueling the accelerated expansion of our universe. And yay, astronomers got a Nobel Prize for discovering this effect. But there's no compelling theory to make us understand where this mysterious source of energy is coming from. And this is one of the major challenges for astronomy, and I'd argue this is one of the major challenges for science today, to understand the dark side of our universe. What makes up 95% of our universe? And what I want to tell you about today is a technique called weak gravitational lensing. On paper, this is by far the best way to understand the nature of the dark side of our universe. And that's because you can go from a really fundamental theory, Einstein's theory of general relativity, and you can work all the way through to what you actually observe, with just one assumption that we will come back to in the course of the next hour. Compare that to other cosmological probes. We have supernovae, which lets us probe the distant universe. but we don't really know how much of a standard candle they are. We have galaxy clustering, which also probe the dark universe, but we don't really understand how galaxies completely trace dark matter. And that's why weak lensing is kind of being touted, or it's believed that it's going to be the most powerful probe in our arsenal of observational cosmology tools in which to understand the dark universe. And so that's what I want to tell you about today. And by the end of today's colloquium, I'm hoping that you will all be convinced that gravitational lensing is the way to go in order to understand this mysterious dark universe. Okay, how are we going to do it? This is a picture from the GEM survey, which Hans Walter said we were working on when I was here, and there's lots of beautiful galaxies. So the first is what we're going to say is that galaxies are going to be randomly oriented in the sky. Now you'll notice there's a little asterisk at the end of this. This is the one assumption that we're going to have to make, and we'll come back to how good an assumption that is. Okay, so galaxies are just randomly oriented in the sky, and their light is going to travel through the universe towards our telescopes on Earth. But in doing that, as the light travels through the universe, it's going to go past lots of overdensities of dark matter. And Einstein's theory of general relativity tells us that mass warps space and time, so the path of that light is going to be deflected as it travels towards us on planet Earth. So we've got a little cartoon here, lots and lots, there's a pointer, lots and lots of dark matter here, we've got some cartoon galaxies there, light's travelling through the universe, and each time it goes past an overdensity of dark matter, it gets bent and distorted. Now, what that means when we observe it from planet Earth is it looks like the galaxies are lining up with each other. Now, I should state that this is really a cartoon, it doesn't really look like this in the universe, just to give you an idea. If you look at distant galaxies, and these are toy cartoon galaxies here, what you find is that the dark matter makes them look like they're lining up with each other. And if you like, you can think of this as a signature that dark matter leaves on the images of very distant galaxies. And it's telling us where the dark matter is and how much of it there is. The more dark matter there is, the more that dark matter will warp space-time, the more light will be distorted, and the stronger the alignment that we'll see between nearby galaxies. So that's the signature that we're going to be looking for. And if you image a big enough patch of sky and you look for this effect, then you can infer where the dark matter is. Now, this is the biggest dark matter map that we've made using this technique. It is about the size, if you hold your hand out at arm's length from the sky, it's about the size of your palm on the sky. It's quite a small patch of sky, but it took us 5 years of data to get this map, this area out. We looked at the images of 10 million galaxies, measure their shapes, and we look for this very weak alignment between them. And then where we see lots of alignment, then we infer that there's lots of dark matter. For example here, so white here is where there's lots and lots of dark matter, and you can also see that there are some void-like regions where there's less dark matter. You can also have a look at where the galaxies are. And what you find is the biggest regions of dark matter, where you see the strongest lensing effect, the strongest alignment in the images of background galaxies, that's where we also see the most massive clusters of galaxies. Okay? So in these regions you see these big clusters of galaxies.
So these are the foreground galaxies?
They are foreground galaxies, yeah. We can look at galaxies on large scales as well. And these are the galaxies in pink, smoothed on the same scale as the dark matter map, and I'm going to blink between the two of them now. So you can see whether our theory that galaxies trace matter, dark matter, is a good one. And in general, you find that there's very good agreement between where the dark matter is and where the galaxies are. And this is exactly what our theory of dark matter predicts. It's the dark matter that dictates where and when galaxies form in our universe. It's the dark matter that houses the galaxies in our universe. So we would expect the dark matter to be distributed in the same way as the galaxies. And this is the first time we've been able to see this on very large cosmological scales. Now, these pictures are all very, very pretty and everything, but this isn't really how we do science. So what I'm going to focus on for the rest of the talk is what we can do statistically with this sort of data to pull out information about the dark matter. Let's start off with a little plot from a paper by Marlin Belander. How much dark matter is there in a galaxy relative to the amount of mass in stars? It's a good question. So this is the ratio between the amount of dark matter and the amount of mass in stars. The data points come from lots of different data sets, but they're all using this lensing technique to tell us how much dark matter there is, and then we can see how much dark matter there is relative to the amount of stellar mass. And we split this up into two galaxy types, red and dead galaxies and blue star-forming galaxies. And you can look at this data for a long time, but just for a rough rule of thumb, for the red and dead galaxies, we've got roughly about 50 times as much dark matter as there is mass in stars. And for blue galaxies, it's roughly about 100. It depends on the stellar mass of the galaxy. So we can use this lensing technique to understand how galaxies evolve and depend on their dark matter environment. Let's notch up the scale and look at galaxy clusters. This is a paper by Kimokatula, I found. Same data set, but now we're looking at the difference between the amount of dark matter and the X-ray luminosity. So this is using Chandra and XMM data to measure the X-ray. So in a massive cluster of galaxies, you'd expect there to be a lot of intracluster gas that gets heated up because of the gravitational potential and then emits in X-rays. And there's a very good relationship between the amount of light that's emitted in X-rays and the amount of dark matter. So lensing lets us look at dark matter on cluster scales and galaxy scales, and it can tell us a lot about what's going on in these different environments. I'm going to come on to the cosmology very shortly. Okay, where's all this data come from? I'll just show you these results from. So this is for the technical people in the audience. For about 5 years, the Canadian and French communities invested essentially all of their good seeing, good weather conditions to undertake the CFHT legacy survey. And this is the data that forms the basis of this analysis. It's 155 square degrees, UGRIZ data. And what you can see here is the camera that was used. Now at the time, when this was first put on the CFHT telescope, which is a 4-metre telescope in Hawaii, this was the largest field of view camera to take observations. Now since then it's been superseded by Pan-STARRS and DES, but at the time this was a very important camera. There are some statistics here which the extragalactic people in the audience will want to know, and you can just read those numbers for yourself. For those of you who are not extragalactic or cosmologists, all you need to know about this data is it's very high resolution. Now remember, for lensing, we want to look at how galaxies are lining up with each other, so we're going to need lots and lots of galaxies to do that. So we need high resolution imaging. We need deep imaging, okay? Now the light from these galaxies is coming all the way through the universe and getting bent and distorted by the dark matter. And so we need to go deep into the universe in order to look at dark matter over a long period of time. Redshifts. If we're going to look at how dark matter is evolving through time, we need to know where it's at. So we need redshifts, and to do that we use photometric redshifts. And we need to be able to measure our data very accurately. So we did spend a lot of work on that. In cosmology, the name of the game at the moment is all about systematics. How well can you trust your results? It took us about 5 years to process this data to such an extent that we were happy with the results, and there's lots of information about that in the papers on this project. So it's the CFHT lens survey. Now, I've been showing this picture of our fabulous team for quite a while, since we first did it, and I've been challenging other astronomy teams to beat us on the Best Dressed Team Award, and nobody has met my challenge yet. So any other teams out there, Best Dressed Team Award. It's a really international team. We've been working on the project for 5 years, so people kind of moved away, but it really covers the whole globe. And I should particularly point out Ludwig van der Becken here, who led the survey with me. But an absolutely fabulous team of people, and it wouldn't have been possible without all of them. Why did it take us 5 years? This survey finished in 2008, yet our first papers didn't come out until 2013. So what took us so long? And this is a big question on lots of cosmologists' mind. I said at the start that lensing is by far, on paper, is by far the best way to understand the dark universe. Yet there was this big gap of 5 years where we didn't publish any papers at all. Why? What took us so long? Okay, let's recap what's happening with this gravitational lensing measurement. We've got very distant galaxies, and their light is going to propagate through the universe and come towards us on planet Earth. It takes about 6 billion years for the light from most of these galaxies to come all the way towards us on planet Earth, and you get these subtle distortions each time it goes past a clump of dark matter that's going to cause these galaxies to line up with each other. Great. 6 billion years this light travels through the universe. In the last moments, the light goes through our atmosphere. And this is an HST image, but some atmosphere. It goes through our telescope, through all the lenses. It lands on our detector. There's noise. All of these distortions add up to about 10 to 15%. Whereas the dark matter, in the first place, only gives us about a 1% change in the shapes of galaxies. To give you an idea there, a galaxy that's circular, if I change its shape by 100%, it'll end up as a line. So dark matter changes the shapes of galaxies by just 1%. Tiny, tiny distortion. Yet the atmosphere, the telescope, the lenses, the detectors, that's a 10% change in the shapes. So if we want to understand what's going on here, in order to probe dark matter in our universe, then we need to understand all of this to absolute high precision. And this is the name of the game. I started all of this work and research because I really wanted to understand the dark side of the universe, and I find myself really knowing an awful lot about CCD detectors, telescopes, and the atmosphere, things that I never thought I would worry about. It's very fascinating. And that's what took us the time, that's what took us all 5 years to process this data, because we had to understand all of this to exquisite precision. I think some of the techniques that we've learned are very useful for other observational tools, people who are working on stars in the Milky Way, for example. How do you separate a faint star from a distant galaxy? Those are the sort of questions that we had to address. So if anyone's particularly interested in that, they can please come and talk to me tomorrow. Okay, I'm now going to get on to the cosmology side of things. Now, the tool that we're going to use to do this is called a shear correlation function. And I'm showing you one example here. What's plotted here on the y-axis is how aligned the galaxy pairs are. And I'm going to iterate for the third time, this is the final time, just in case you missed it. What we're looking for is an alignment of the galaxies, because if I've got two galaxies that are close to each other, as their light travels through the universe, it's going to be bent in the same way, so it's going to look like they're lining up with each other. Galaxies that are close to each other on the sky are going to be more strongly aligned than galaxies that are further apart, because if I've got two galaxies that are far apart, their light's going to travel past different large-scale structures, so they'll experience different distortions. That's why you get the curve that looks like this. Now, you'll notice there are some other lines on here. I said at the start we were going to make an assumption that galaxies are randomly oriented. But let's imagine that there's a lump of dark matter over here, and another lump of dark matter over there, and I'm a galaxy forming in between these two lumps of dark matter. In the simplest model, I'm going to form looking like that, pull towards the two dark matter clumps. Now, let's imagine that there's another galaxy forming nearby me. It's going to form in the same shape. So we expect that galaxies that are physically very close to each other, they will actually be aligned with each other. So we need to disentangle the alignment that's introduced by dark matter from the intrinsic alignment, what physically happens to galaxies when they form. And this is the first time we've been able to do this with this survey, and what we've done is we've used a model to account for this intrinsic alignment effect, and we fit the data simultaneously. So we fit, this is our data here, the data points here, how aligned the galaxies are as a function of their separation, and we fit these data points with a model that includes both the dark matter and the intrinsic alignments of the galaxies. And yes?
You have just told us that the distortions in the alignment are 1% effect. The y-axis is vastly smaller numbers.
Yeah, so 1% is the change on a single galaxy, and this is how. So this is the square of that. So it's how aligned they are. So yeah, as you tend to find. Okay, but how am I going to disentangle these two things? I can't just do it with one redshift bin. So what we do is we look at lots of different combinations of redshift bins. I've got 6 different redshift bins here. Let's just guide you through this wealth of data. Each one of these, let's go along the diagonal here. So I've got 6 different redshift bins from a redshift of 0 all the way up to a redshift of 1.2 up here. And I can look at the correlations between the galaxy shapes, lots of different redshifts. And also, like up here, this panel, I'm looking at the correlation between galaxies at low redshift and galaxies at high redshift. And it's the combination of all these different cross correlations that lets me disentangle the 2 different effects here. I think this really is important because this is the one niggle with gravitational lensing. We have a very, very pure theoretical understanding of what we should observe here. We just go from GR and we can populate that through all the way to what we observe. But we've got this nasty astrophysical bias here that galaxies can intrinsically align. And I think we have to understand that in order for this probe to reach its full potential. And because there are some intrinsic alignment enthusiasts in the audience, this is one of our results. So not only can we constrain cosmology, but we can actually see how aligned the galaxies are. This is split into red and dead early type galaxies and blue new star forming galaxies. All of our parameters are degenerate with each other. So on the x-axis here I've just got the amount of dark matter. And on the y-axis this is a parameter that controls the amplitude of how intrinsically aligned those galaxies are. Don't worry too much about its value, but what I wanted you to take away from this is that we detect a significant alignment between the early red and dead galaxies. And this has been seen by SDSS as well. This is the first time we've been able to see this at high redshift. So it's true when for red galaxies forming in the same environment, they do intrinsically align with each other. So even if you don't care about the dark universe or cosmology and you're really interested in galaxy evolution and formation, this is a really interesting topic, I think. Blue galaxies, we've got no evidence for intrinsic alignment, but that's potentially because our model that we're using, lump of dark matter over there, lump of dark matter over there, and the galaxy forming in the middle, is probably too simplistic. So we need to improve our model there, and I think Bjorn is going to help me with that project. Okay, cosmological parameters. Lensing is sensitive mainly to how clumpy dark matter is, which is this parameter here, sigma 8. If sigma 8 was really, really high, you'd have lots and lots of clumpy dark matter and lots of big voids. And if sigma 8 is very low, then the dark matter is spread out isotropically. That's this parameter here. And on the x-axis, we've got how much dark matter there is, omega m. And lensing is, shown in pink here, it can't really distinguish between these two. It can't distinguish between there being lots of concentrated dark matter or just lots and lots of dark matter. So that's why you've got this banana here. In blue, we've got the results from WMAP for these 2 dark matter parameters. In green, the results from baryoacoustic oscillations, that's looking at how galaxies cluster, and in white, everything combined together. So we were super duper happy when this result came out. We did lots of careful blind analyses beforehand, so we didn't have confirmation bias, and all was well for about 4 months until Planck came out. And we are one of the many cosmological probes that do not entirely agree with Planck. There is tension between our results and the Planck results from the CMB. Just orientate your gaze, the same parameters, sigma 8, how clumpy the dark matter is, or how clustered it is, and how much dark matter there is in total. Pink is the results from the lensing, blue is the combination of WMAP with the lensing, and purple is the constraints from Planck. So we had a brilliant summer where there were lots of conference talks, and George Staffio would give his fantastic talk about Planck, and absolutely fantastic, testament to how excellent Planck is. And then the rest of us would all nervously stand up and show our results, waiting for the question which would imminently come. And there was George in the front row. What is wrong with your analysis? So there is we don't really know what the baryons are doing to our data. And I think that's what we have to understand better. At the moment, all of our analysis is based on dark matter-only simulations, and I think we need to put baryons in there. But also, it sounds like the Planck results are changing as well. There's been reanalysis of the Planck data by the Princeton team, and actually that brings the Planck results in much better agreement with the lensing results. Let's wait and see what the next Planck analysis brings in November, and in the meantime we're also working very hard on new data. Okay, I've talked so far about dark matter, but actually I'm much more interested in dark energy, because that makes up about 70% of our universe, and we really don't have a clue about dark energy. There's a lovely movie here by Jan Hartlap, and what I want you to take away from this is just how we're going to use this lensing data, which probes dark matter in our universe, how we're going to use that to tell us about dark energy. Now there are two simulation boxes here, the lambda CDM, which is kind of our best guess of where we are at the moment. That's dark matter and dark energy. And on this side, SCDM, that's dark matter alone. Now I should say that we've already ruled out this model, but it just gives you a visual impression of the differences between when you have dark energy and when you don't. Now if you ever have the pleasure of giving a talk to a bunch of school kids, I'd like to explain dark matter and dark energy kind of like some dark sibling rivalry. So dark matter, the gravity of dark matter is pulling everything together. It's trying to make these structures grow, and you can see that in this simulation on the right-hand side. Very early on in the universe, the structures have already formed. The gravity of the dark matter is pulling those structures together, making them much more concentrated much earlier on in the universe. Now what happens when, and if you're talking to school kids, it often gets a laugh if you call it an evil twin sister. But when dark energy comes along, it kind of changes the playing field, because it makes the distances between galaxies further apart. As dark energy kicks in and accelerates the expansion of the universe, it makes it harder for dark matter to pull those structures together. So what dark energy does is it slows down the growth of these dark matter structures. So what you can do is you can use lensing to map out dark matter at different epochs in the history of the universe, and then you can see how those structures are growing. You see, in a dark matter and dark energy universe, the structures form much later. And you can use that to test dark energy. The audience are heckling and objecting from the front. No? Good.
The acoustics are dangerous of this place.
What I've got here is, again, the lensing data. This is how aligned the galaxy pairs are, but now I'm going to plot it as a function of redshift. So galaxies that are much further away, they're much more strongly lined up with each other because their light travels through much more dark matter, so they experience much more lensing. And you can use how this lensing signal changes with redshift to tell you about dark energy. And that's one of the really unique aspects of lensing. It's really probing how dark energy is changing the growth of these dark matter structures. So we've got constraints on W, this is the equation of state of dark energy. And we can also let things vary. So all of the plots that I've shown you so far, we've assumed a flat cosmology, which is kind of our best guess. But you can let the curvature change. If you do that, CMB here, which is in blue, CMB finds it hard to constrain things as soon as you allow curvature of the universe to vary. So adding in these additional data sets really does tell you new information. Okay, I said at the start that we have some pretty good guesses about dark matter, that it's a weakly interacting matter particle, but that we haven't found it yet. So what about dark energy? What could be causing this accelerated expansion of the universe? Now, the simplest explanation is that the vacuum that permeates our universe has an associated energy with it. Now, when somebody first said this to me, I was like, what? I have no idea what you were talking about. So I probed these theorists. I was going to, please explain this to me. And quantum field theory tells us that in a vacuum, you can have virtual particles that pop into existence, and in doing so, add energy to the universe. Now, you can imagine this almost like a perpetual motion machine, because the faster the universe expands, the more vacuum there is created, and the more opportunity there is for these virtual particles to pop into existence, thereby adding more energy into the system, thereby causing the universe to expand even faster. And it's a very elegant theory, and you can detect this effect even in the lab. But the problem is, if you then ask your particle physics theorist to calculate exactly how much energy this vacuum effect would create, it's the famous 120 orders of magnitude different than the dark energy that we measure. So the simple and simple, elegant explanation for dark energy just doesn't seem to work. I mean, come on, astronomers often disagree with particle physicists. We have a long history of disagreeing with them, but 120 orders of magnitude disagreement? Yeah, that's going to be a difficult one to resolve. So this is often called the cosmological constant. They can be used interchangeably. Now, some people would say this is still kind of the best guess, but its theoretical grounding is hard to reconcile with the observations. And that means that basically the theorists are going wild with their ideas. A new scalar field. And the way I like to think of this is, we know in the very early universe there was a period of rapid inflation that was caused by a scalar field. It could be that some physics like that is happening again, that's causing a new period of inflation in our universe. Then we've got all of the crazy, wonderful models, colliding brain worlds and multiverses. I particularly like the multiverse model because I love describing it as the... Do you have aero bars in Germany? Or is this a British chocolate bar? Oh, how disappointing. It's a British chocolate bar. It's a British chocolate bar with lots of little...
British souffle, I think. It also exists here.
Bubbly, lovely, what's it called?
Milk souffle.
Excellent. It's like a chocolate bar with lots of little teeny tiny holes in it. Yeah? Okay. So that's kind of like your model of the multiverse. There are lots and lots of different multiverses, and we're just one universe inside that aero chocolate, lovely, bubbly chocolate bar. Now, I used to be really negative about the multiverse model until the fabulous Andrew Liddell said that it was a natural outcome of inflation theories in quantum field theory. So it's there, it's potentially out there, that there are just lots and lots of universes in there, and we just happen to be in one that's got a really freaky cosmology. So that's one I think. What I want to tell you about next is the thing that I'm most excited about, because I really like the idea of walking into work every day and thinking, well, I'm going to play with Einstein's theory of general relativity today. What better way to start your day than to confront the best mind in the history of physics? Do we need to go beyond Einstein's theory of gravity? And none of the above. There are tons of theories out there, and I think that what's really exciting is we just don't know. Let me tell you about going beyond Einstein. Now, Newton started off with his first theory of gravity. His theory of gravity went a bit like this. Gravity is stuff attracts stuff, and that the way it does that, there's a fundamental constant. Now, Einstein came along and he said, no, it's not stuff attracts stuff. Gravity bends the whole of space and time, so things just kind of roll together. But it does this in a fundamental way through the universe. G is a fundamental constant. So the plethora of modified gravity models, or beyond Einstein gravity models that are out there, are basically saying, does gravity bend space and time in the same way? Now, we know from our own experience that space and time are quite different, because I can move any direction I like in space, but I can only go one direction in time. So maybe there is something fundamentally different between space and time, and maybe gravity bends them differently. Is big G really a constant? What says that it can't evolve with time or with scale? And these are the sort of questions that we're asking. So we are extending general relativity to give it a bit more flexibility to do that. Now, I've got usually at this point in the seminar where somebody shows a formula, I go, ah, and switch off. Please don't do that, I can explain this formula. Okay, this is the space-time metric. It tells you about how light and objects move in different gravitational potentials. Now, these two signs here tell you about the gravitational potential, and in Einstein's theory of GR, these two things are the same. Mass bends space and time in the same way, and you can relate the gravitational potential to the density field. Okay, so as you can see already, some of you have switched off. The density field is just how much mass there is in different locations across the universe, and it's that mass that's bending space and time. Now, we know that GR works incredibly well on solar system scales. So if we're going to be tinkering with GR and we're messing around with it, then we need to make sure that we don't mess around with it on the scales of the solar system. So we're going to have something that changes on large scales. Now, what we're doing is we're changing Poisson's equation. So we're saying this term here is basically saying that big G varies with time. So A here is the scale factor of the universe. And we're also saying we've got another term here that says that mass can bend space and time differently. Now I'm going to use two data sets in order to test out this model to see whether we've got any evidence for this change in GR. Up here we've got the lensing data. This is how aligned the galaxies are as a function of their separation, and we've got two different redshift things here. And the different models that you can see here are just the different ways that we're changing GR, how we're letting it bend space and time differently, and how we're letting big G evolve. Now at the bottom here I'm going to use redshift space distortion measurements. Now, with lensing, light travels through the universe, and it travels through as much time as space. So it's sensitive to both to how gravity bends space and time, because it travels through as much space and time. Now we can also use galaxies to probe dark matter in our universe, because it's the gravity of the dark matter that pulls those galaxies around. But they don't move through very much space. So imagine galaxies in a big cluster. They are moving, but they don't move through very much space, and so they're just sensitive to the time part of the potential. I'm using these redshift space distortion measurements to just look at the flow of galaxies relative to the dark matter. And this is our result. This is a paper by Fergus Simpson. It's absolutely fantastic theory person who I managed to persuade to do some observations with me. Here we're looking at the deviation in the time potential, so how mass bends time, or gravity bends, warps time. And here we're looking at the difference relative to GR of how mass bends space. So the redshift space distortions here in green are just sensitive to the time part. And in red, you've got the constraints from the gravitational lensing, which is sensitive to both of these potentials. We combine these together in blue, and in white we're also adding in information from the CMB. Now, when Fergus and I were doing this, we thought this was such a fundamental thing. We better absolutely test everything out first on mock data. So we developed all of the pipelines on mock data, we made sure that everything ran first, and we were determined we were only going to run this on the data once, because we didn't want to have any cosmological biases in our opinion. And it was right before Christmas, actually, when we finally ran on the data, and I'm not sure who was more nervous, him or me, just waiting for those chains to finish, because I didn't know what I wanted, whether I wanted to find something that was different from GR, which would have been like really groundbreaking, or whether I didn't want to, because we could only run on the data once, and if I found something different from GR, oh, did that mean my data was wrong? Anyway, this was just run once on the data, and this is the result that we got. GR is this cross in the middle, so no deviation from GR. So our results are nicely centred on that. And I think this is really a sign of things to come. Like, this is a really small patch of sky. Imagine we've used data that's just about the size of your palm on the sky. And we've got the whole sky to survey in order to do this sort of experiment. This is a really unique way of testing gravity for the first time on the largest scales of our universe. And I think there's lots more exciting things that we can do with this and expand our models of beyond Einstein gravity to really test all of the other different models that are out there. There are lots of different modified gravity models out there which we can test with this sort of data. All of our data is public. You can download all of our data, right from the reduced images, PSF models, catalogues, photometric redshifts. If you don't want to get your hands dirty with data or pixels, you can just download our covariance matrices and our data points. We have now hit the point where there have been more papers published with our public data than the team actually published themselves. And if you're in a survey of your own, I heartily encourage you to make your survey data public. It is really important for the community and also really important to you, because there's something about making your data public that makes you be really certain that you've done a good job for it. cfhtlens.org, if you want to download anything, please email me if you've got any questions. So there are a ton of people working on this data at the moment. I think it's a really great data set, and I encourage you to use it. In the last 5 minutes, I would like to tell you about what's coming up next. This is a lovely plot from an ACT paper, and it's showing you all of the different surveys that are coming up. And the combination of, I think the next big thing is going to be combining all of these probes together. So I've already shown you how I can use how galaxies are flowing and lensing to probe modified gravity. I think the next big thing is to add in CMB. So this is a deep ACT pole field where it's looking at very high resolution ACT data in B modes as well. And there are 6 of these fields here in pink. And you can see that there's lensing data that's going to cover all of these fields. And I think the combination of this data together is going to be really powerful.
Can you tell us what ACT?
ACT, yes. Atacama Cosmology Telescope. So it's kind of like Planck, but on a much higher resolution. So it's just looking at small patches of sky. So it's still looking at the CMB, but there are very, very more high frequency variations in the CMB. The project that I'm working, there are 3 big imaging surveys that are happening at the moment, and we're all competing with each other gloriously. The Europeans are in charge of KIDS, which is the kilodegree survey, and I have the happy pleasure of coordinating the data analysis team with Colloquium, Massimo Viola and Hendrik Hilgren, fabulous team. These are them all. The Japanese, meanwhile, are competing on the Hypersuprime CAM survey, which is going to be here. And the US and part of the UK, and I think, I'm not sure, I've got DES here in the south. Now these are big imaging projects. DES is going to survey 5,000 square degrees, so it's 30 times the area of the lensing survey that I've already told you about. It's going to be phenomenal. So there's going to be big things happening in the next 5 years with these 3 surveys. Let me tell you about KIDS, because this is the European project. It's an ESO public survey. You can grab the data the moment it's taken from the telescope, or you can wait until we process it and grab it off the archive a year later. It is a fantastic camera and data set. There's a history here at MPIA of VST and the traumas, the 7 years of bad luck after the primary mirror shattered in transit to Chile. had VST not had all of those traumas, it would have been absolutely groundbreaking, but it still is going to be a really major survey because the camera that we're using to take this data is absolutely phenomenal. Remember I was saying that the light travels through 6 billion years of our universe and then it gets all bent and distorted at the last minute by the telescope and the camera. Those distortions are really very, very weak for this telescope and camera because it was designed specifically for this purpose. So it's going to be a great data set. Really early kid science. Here's that shear correlation function. I was telling you about how aligned the galaxies are as a function of their separation. And in black is the lensing signal. And in blue is the B mode. The B mode tells us about how well we've got rid of all of those other horrible little distortions from the atmosphere and the telescope. And we're doing really well. It's consistent with 0 on all scales. And we didn't have to work too hard at this. Here we've got data from a spectroscopic survey called Gamma, which allows us to identify galaxy groups, so we can look at the mass of the group as a function of its luminosity. There's lots of exciting things that's going to come out of this survey, and this is a public survey, so you can grab it all yourself. What's coming up after that? This is a fantastic slide that I stole from the wonderful Megan Gray. These are some images of Combo 17 galaxies, imaged from Chile. And here are the same galaxies, imaged by HST. And I'll just do it again, because Megan did such a good job of it. The atmosphere is our enemy when it comes to these sort of measurements because it absolutely blurs everything out. If we're wanting to look at these tiny distortions that dark matter is leaving on things, getting above the atmosphere is just fantastic. And that's why we're all super duper excited about Euclid. It's going to be launched the next year. Imagine it, I like to imagine it like Hubble Space Telescope quality imaging across the whole sky. It is going to be phenomenal. But what it lacks is the colour information. We need those redshifts. If we want to look at how dark matter is evolving through time, then we need to know the redshifts of our galaxies. And Euclid isn't going to tell us that. So, LSST is going to happen. Same sort of timescale. Now, LSST is going to survey the entire sky every 3 nights. And not only is it going to unveil the mysteries of the dark universe, but it's also going to find all of the killer asteroids, so we can mobilise Bruce Willis to go and get rid of it. It's going to be fabulous. The UK is currently deep in petitioning the government so we can join as a country. And I do believe the Max Planck people are thinking of joining LSST. As I'm sure. Anyway, it is going to be an absolutely fantastic project. The combination of these two surveys together is going to tell us an awful lot about the mysteries of the dark universe. And I'm hoping, seeing as I still have 35 years till I retire, that I might be able to see these two projects through to their conclusion so that eventually I can tell my son, after however many years of research, that I do finally understand what I'm talking about. At this point I would love to do an audience poll, but unfortunately I think we're going to run out of time and I'd rather have questions from you. But when I did this audience poll with my fabulous class of undergraduates, usually they were split. I think most of them went for we need to upgrade our theory of gravity as their reason for, or what they thought Euclid and LSST would discover. And that's probably because I was really selling it, because it's what I'm particularly excited about at the moment. But there were a few of them who voted for none of the above. Happily, not many of them thought the astronomers had got it wrong. But a few of them had asked for none of the above. And so I asked one of them, what do you think it's going to discover? Now this was one of my particularly miserable and depressed undergraduate students, and he said to me, well, Catherine, Euclid is going to blow up on launch, so it's not going to discover anything. And LSST mirror is going to break just like your VST mirror broke, so it's not going to discover anything. So I hope that that is not the case, and I think these two projects together are going to be absolutely phenomenal. If you take nothing else away from this fabulous time that we've spent together, I want you to take away the thought that this dark universe science is really important. I mean, if it's really pointing to something as fundamental as GR isn't our complete model of gravity, then this is really, really very exciting. I think we're going to learn a lot about lots of other areas of science from the projects that are going to answer this question. And I'm a firm believer that lensing is going to be the major component in completing our understanding. And thank you for your time. Thanks very much.
So, thank you very much, and now it's open for questions.
Your constraints of alternative gravity models, how did you calculate your expectation?
How did I calculate my expectation?
You need to compare it to something.
What were my models?
Or the data, you have to compare them to models. I'm wondering what the lensing model is alternative gravity models.
Okay, so we are, yes, we're being a little bit naughty in that these lensing... so lensing is very sensitive to small scales when nonlinear effects start to happen. And the Einstein models are only really correct for linear scales, but we just propagate, we have a modified gravity power spectrum and then we propagate that through the lensing equations. So,
how do you get at that?
How do we get at that? So we have these, take these two equations to define the different Poisson equations, and then we change the mass power spectrum accordingly.
So you run simulations?
Well, no, they're theoretical models. So you tweak the mass power spectrum and then convolve it with a window function to get the theoretical models, which are these ones here. So the dash line, the dot dash line are different parameterizations of the shear correlation function in these phenomenally logical modified GR models. But in principle, it shouldn't be done on these scales. Really, it's only the largest scales that we should be using. And you'll note that we don't use a lot of the data down here. We're mainly using these large scales. So what I want to do next is go out to even larger scales. So this is limited up to about 30 odd minutes, and the current data that we're working with are going out to 6 degrees, so really that's very, very large scales.
Okay, further questions? Or do you want to?
No, just
okay.
Just to follow up on that, so you have a general reflection angle in that theory, a general expansion history of the universe and such?
Yeah. So the other part that I didn't say is the how we let these two parameters evolve. We say that our best guess model is lambda CDM, and so these two degrees of freedom that we allow the model evolve like lambda, or then lambda-like evolution. And that's the next thing that we want to include as we build up our data set, is to make that less. I mean, that's quite a constrained model that we're putting in there, so we need to allow that more freedom as well. But it's just a tiny patch of sky, so baby steps. So I think, yeah, it could be really exciting.
So there are many dimensions in which surveys could improve from current day parameters, and it sounds like LSST and Euclid. LSST plus Euclid will give you your cake and let you eat it as well. But going from current day measurements, which dimension would you go after? Area, depth, seeing, or color information?
So I think SKA is going to be the next big thing on the horizon after Euclid and LSST. SKA is a big radio square kilometre array project. And so I said for lensing, we really need to know the redshifts of the galaxies, because we want to look at how dark matter evolves. And with SKA, we're going to get really, really accurate redshifts for everything. And provided the configuration is right, we'll also get very, very high resolution images of the galaxies, and which isn't affected by the atmosphere and things like that. And you model the radio telescopes very accurately. So all of the things that we have to worry about for optical lensing are less challenging. In addition, I'm saying we're worrying about galaxies that are intrinsically aligned with each other. Now, in principle, you can use the polarization of the radio measurements to give you an indication of what the intrinsic shape of the galaxy is, as stuff done by Michael Baum and Richard Batty. And that is going to also help. So I think SK is going to be the next big thing after LSST and Euclid. In addition, the Americans are building something called AFTA, A-F-T-A. It's a great project, actually. There's some old spy telescopes or something.
It's now called WFIRST.
It was called WFIRST, but it's now called AFTA.
Okay.
Because it's afterthought. Anyway, so WFIRST was going to be like a 1 metre telescope, but then some spy agency or something said, hang on, we've got this 2 metre telescope that we were pointing down, and now we can point back out again. And if it happens, that is really going to be quite phenomenal. At the moment, it seems to be some morphing between exoplanet research and cosmology, and I'm not sure the compromise is going to work to make it excellent for cosmology, but in principle, a big 2 metre telescope up in space could do even better than Euclid. Euclid's only really going to go out to a redshift of 1, so if you've got some really early universe dark energy model, Euclid isn't going to be able to detect that, so yeah. Actually, what I want to do, so this was one of the questions I gave to our PhD candidates, is if you had unlimited resources, what would you do with them? And one of them actually turned the question back on me. I said, oh yes, what would I do? But I would build a liquid mirror telescope on the dark side of the moon. That is what we need. But I probably would have retired before that happens.
I think the two next big projects that you mentioned are largely based on getting the type of information we have now just on vastly larger areas.
Exactly.
That's the one point that you also said, oh, it's all about systematics. So in which effect, either physically or data analysis, do you think is most dangerous to the optimistic square root n scaling?
Okay, one big plus we have for kids is the near-infrared data. So redshifts are as important as measuring this alignment of galaxies. If your redshifts are wrong, you'll completely misinterpret your signal. And the near-infrared data that we have with kids, that comes from the Viking Vista survey, we've got 9 bands to get our photometric redshifts. That's going to really help us understand whether a galaxy is actually really close to us or really, really far away. That degeneracy between low and high redshift. I think that's going to be an important step forward. And just, yeah, the quality of the data. So really being able to understand what's going on the detector level. Particularly for kids and DES. And indeed, Hyperscreen, all of the 3 cameras were built specifically for this task.
So you think, in the end, the limiting factor is that our sky only has 4 pi steradian?
Yes.
Gary of the galaxy, and we have more.
Maybe, I mean, on a theoretical level, we don't really understand what the baryons are doing. So we can, all of our results depend on understanding what theory would predict, and baryons kind of complicate that. So maybe it's computer power that will limit us in the end.
Other questions? I saw one hand before.
So nothing gives you this shear, right? But it's also giving you magnification.
Thank you for giving me the opportunity to talk about magnification. Yeah, so I have a fabulous PhD student at the moment, Chris Duncan, who's working on precisely this question. So as the light gets lensed, as it comes towards you, it gets bent, galaxies get bent and distorted. So imagine I'm radiating light. If there was a big clump of dark matter between me and you, then it would lens the light from the back of my head towards you, so I'd actually appear brighter. So lensing both increases the brightness of objects, and it also increases their size, or decreases if there's less dark matter. And that's an additional factor that we can add in for free with all of this data. And the only reason why we haven't done it so far is, I think, lack of resources. So this is something that my PhD student Chris Duncan and Alan Heymans and Benjamin Cooney are working on with me. And yeah, I think it could be just a really good additional add-on, particularly if you use the sizes of galaxies, not just the brightness. But it's Hendrik Hildebrand as well is really working on this in Germany. So watch that space.
Okay, further questions? No, then I would say let's thank Anthony again, and